scale height, the disk will be basically pushed down. And so it will oscillate and eventually reach a steady state in which it's not stable. However, interesting things happen when the X-ray penetration depth becomes greater than or equal to the scale height of the disk. Here, the dynamical time scale for thermal processes via heating to happen will cause the disk to be extremely unstable, because once this disk puffs up here, the pressure gradients from the scale height will not be sufficient to keep the disk stable. And so what happens is that you get this crazy process where the disk basically rips itself apart, on the order of hundreds of years. And normally, at this stage in the disk's life, there's roughly 1 to 10% of the disk mass left. So the lifetimes of these things are about anywhere from 1 to 50 million years, depending on what parameters you set up. So it's kind of crazy that this model predicts that 90 to 99% of the disk takes about 50 million years to dissipate, and then 10% to 1% dissipates on the order of hundreds of years. So it's a really strong cutoff in the predicted lifetimes of these things. And now I will show you a video of how thermal sweeping, or what thermal sweeping looks like. So again, this is the truncated disk. So it's symmetrical over this boundary, so you can imagine it being projected down here. The star would be around about right here, and this whole simulation takes over the place of about 300 years. And it's being heated by X-rays. So and yeah, so it's an extremely efficient method in dissipating the disk. So my work was basically, I derived the equations of the system and then programmed a simulation using Zeus MP. It's a grid-based magnetohydrodynamics code written in Fortran 77. And so I was looking at 3 parameters. Disk models are very well defined in terms of their density profile. So their density profile is based on the radius of the disk, or the radius of the boundary, so how far the disk is away from the star, and the peak mass of the disk. You can basically come up with the entire density profile on those parameters. So I was looking at what happens, or like what densities are required to create a scale height roughly equal to the X-ray heated region. Because that's the threshold at which you would expect this process to occur. And so I made lots and lots of simulations across different X-ray luminosities and across different hole boundaries, I guess it's called, to come up with this delta over H ratio, the X-ray heated region over the scale height. Once that equals 1, you take this density and you call that the critical density. And so what we're doing is we're characterizing the threshold upon which a very non-linear and chaotic system becomes unstable. And so when I was doing this research, I was not expecting, to have nice results. I was expecting that I would get, some crazy function for this critical density, because this whole system is like extremely chaotic, like as you saw in that simulation. But I get like a line, which is amazing. So the critical surface density is like basically you take a point, you take a radius and you integrate above the scale height. So it's like a vertical sheet of density. And so you can, by integrating that across the edge of the disk, you basically get mass of the disk. So critical surface density is proportional to mass. Yeah, so I get that it's proportional to 1 over the radius boundary. This is in log space, right? So, and then I get, in terms of X-ray luminosity, I get that it's directly proportional to X-ray luminosity, which is kind of a really cool, beautiful result. Because then you get, in log space, you get a thermal sweeping plane. So if your parameters of radius, X-ray luminosity of the star, and your density, your peak density, are on this side of the plane, then your disk is stable. And once your disk evolves to this point, it's unstable and it basically dies within a couple hundred years. Very short dynamical time scale. And so the current models predict that a critical surface density for thermal sweeping is something like this, which is not dependent on the radius at all, which surprised my supervisor and me as well. The X-ray luminosity dependence was kind of expected because this temperature, the X-ray heated region, has a weak dependence on X-ray luminosity. The problem with this assumption, though, is that it assumes the entire temperature of the X-ray heated region of the disk is constant, but it really isn't. This is like this is the profile of the disk. So here we have the dust heated portion of the disk. This is the X-ray heated region. As you can see, it varies over 2 orders of magnitude. So that was basically the entire summary of my project. I found out that the critical surface density for a disk to become unstable is directly proportional to the X-ray luminosity and inversely proportional to the radius of the hole boundary. And the importance of this work is basically it provides a lowest upper bound on planet formation timescales. So obviously once the disk is gone, planets can't form in it anymore. And also, just because we want to understand how these disks work, we have a very good upper bound on their lifetimes as well, which is great. And so now all we have to do is wait for the observations to come in. There's a group in Princeton, for example, among many others. Currently we have about 50 disks that are imaged, and this model kind of fits with them all, but of course we'd like more data. And yeah, so I would like to thank my supervisor, James Owen, for letting me work with him. It was a great experience. I'd like to thank the Canadian Institute for Theoretical Astrophysics and INSERT for the grant, and I'd like to thank the audience for listening to me talk about something I thought was really cool.
Do you have any questions for Mathias?
So if the gas are, say, if the disk is unstable, what happens to the material once they're dissipated?
So, like, everything that's heavy enough, like, obviously planets and stuff won't be affected too much. This is basically just the dust, or sorry, the gas of the disk leaving. So heavy dust fragments will remain. So anything, I guess, okay, anything probably greater than like a planetesimal will probably be unaffected, I'm gonna guess. Obviously, like in our solar system, we know that there's the dust, there's like dust in our solar system. So I'm gonna guess that it's largely unaffected. And there's going to be some transport processes, of course, which will kind of make the dust move around. But yeah, when I talked about at the start that thing on gap formation, that would be something to look into, because that when planets form, a gap forms in the disk, and that creates crazy instabilities. Like the planets can transport in and out. Because we're finding that a lot of really large planets are found really close to the sun, and that's very unexpected based on these kind of models. So a huge thing is kind of in planet migration. I had a friend who was sitting beside me who was working on that. It's really cool. I'd ask you to look into that.
Any other questions?
Yeah.
This model was only taking into account the X-ray effects. Does it change also like include the UV?
Oh yeah, sorry. This includes the UV as well.
Oh, it did.
Yeah, but towards later lifetimes, the X-ray kind of dominates over the UV.